or I can have at most the cardinality of S, which is the number of points, right? Okay, now the user decides upon V false and V true. These are user decided constants, V false and V true, and they are fractions, okay? Now, if I want to hide a 1 in here, this means I would like to change the number of points here to map into into this region. Oh, so let's assume I want to embed a 0. I want to embed a 0. This means I would like to change the number of points here such that they map to a number here. Like for example, if this is 5, you see the pointer, right? If this is 5, and I start up with these number of points here, 10, I would like to reduce them to be less than 5. So I will be varying the data such that I am playing with the number of points here. This is if I want to embed a 0. If I want to embed a 1, I would like to change the number of points here to map in this region. Very simple, actually. You know, they are only playing with the number of points here. But what complicates this problem is your reference is not constant. What is the reference again? The reference is a function of the mean, which is the average of the numbers, and the standard deviation of the numbers. So if you are going to embed, to increase the number of points here or decrease them, this means you are going to move some points. Say we want to increase them. This means that I'm going to move some points across the border, right? Across the reference. But as you are moving points across the reference is also moving. So that problem is not that trivial. So in Radu's paper, or in this paper, when they discuss how they are going to manipulate the number set, it's not very clear. What they do is they choose the number of points, the points which are closest to the reference, and they try to move them across the reference, either from the right to the left or from the left to the right. But the main idea is you are trying to change the number of points on the right of the reference, either increasing them or decreasing. Okay. So how to avoid using the primary key? So what did I show you here? I showed you a technique. If you have a list of numbers, I can hide in this list of numbers a 1 or a 0. Okay? Yes?
Where are the user constraints?
Yeah, I will show you. Yeah, the user constraints are enforced when you are changing the points.
Okay.
Yeah, so when you are changing the points, the user constraints will constrain the amount of movement for each point. So, for example, if you try to move this point from here to here, the user constraints may not allow you, right? So the user feasibility constraints, they devise a feasible region of all the points which they can move, right? Such that the usability is not affected yet. Yes. Yeah, good question. So how to avoid using the primary key? They have a very ad hoc solution. The ad hoc solution is, given a number set Si, generate the normalized Si. How? What do they do is, the normalized is, you get Si and divide it by the maximum of Si. This division means that each item of Si is going to be divided by the maximum of Si. So now this maps the numbers to a region from 0 to 1. So now the numbers are normalized. And then what do they do is, for each number Sk, okay, this is not in. For each number Sk in the normalized set, use the first n most significant bits as the primary key. So they use the most significant bits of the number as the primary key. The good thing about this is that the most significant bits are not going to change after you alter your data. And the probability of them changing is very low, right? That's number one. That's the advantage. The disadvantage is, now the user, from the numbers, the user can have an idea where are you hiding things, because he now knows that you are using the most significant bits, and he can devise statistics to find what numbers group with what numbers, and then what numbers are in the same partition. Let's see. So now let's talk about the decoder. When I say r.p, I mean the primary key, which can be either a primary key in the relationship, or it can be the primary key derived using the most significant bits. Okay? So now, the first step is to compute the MAC for each tuple. We have done this before, right? So for each step, we derive the... Yeah, another assumption here is that the relations are a single attribute relations. This means you don't have multiple attributes. You only have one column. Actually, you can have two. One as a primary key and one as the numbers themselves. Or if you don't have a primary key, it will be only one column. Okay? So after you generate the MAC for each tuple, you sort the tuples according to the MAC. Make sense? So we sort the tuples according to the MAC in ascending order. So now we have the tuples sorted according to the MAC. Now I have the numbers are sorted, right? Now I have to split them into partitions. And each partition is a number set. And each number set will handle 1 bit. Okay, so what do we do? How to locate the partitions? So you have max, 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 max. So what you do is you locate the max that result in a 0 when the modulo is taken. So r.mac equals 0 says that this is a marker. And the data between two markers, tuples between two markers, are referred to as partitions. So tuples between two markers are in the same partition. So the first step, we sort. The second step, we partition based on the MAC. And the last step is bit embedding. How do we embed a bit in a list of numbers? We have partitioned them. It's a list of numbers. What do? We embed using the same technique that we described 2 slides ago. Make sense? So the first step is you sort in ascending order according to the MAC. It's a very simple slide, but maybe it will help. Then we locate the MACs. We locate the markers. How do we locate the markers? Is r.mac equal to 0. The yellow ones are the markers. So the values between two markers is a number set. This is a partition. And then what do? We embed a single bit in each partition. How do we do that? By varying the statistics. See? So for example, in this partition we have embedded a 0. In this partition we have embedded a 1, 0, 1, blah, blah, blah. How are we embedding? By varying the statistics. Let's talk about the decoder. Very symmetric. What do we do in the decoder? We sort and partition the same way, right? Because we have sorted and partitioned to find the partitions. We do the same thing. So partition the data set using the same approach used in the encoding phase. And then bit detection. What do is we look at the violating set. We compute V of C, which is the number of points to the right of the reference. And accordingly, we decide, is it a 1 or a 0, right? Another thing is, to compute the number of points to the right of the reference, what do you need to compute? You need to compute the average of the numbers, which you can compute from the numbers you have. You need to compute their standard deviation. You can also compute it from the numbers. And you know C, so you can find your reference, right? After you find your reference, you just count the number of points to the right of the reference. If the number of points to the right of the reference fall in the first region, this means that it's a 0. In the middle, it's undefined. And on the right, it's a 1. Let's see here. We will talk about the second step just in a while, but just in the next slide. But the third step is majority voting. I can have a lot of partitions. This means I can hide one bit, a certain bit, multiple times in the relation, repeatedly. This means when I'm decoding, I will be decoding this bit several times. So how will I decide which one is the correct one? So I use majority voting. Majority voting means that I will select the bit that occurs the most. Okay. So let's see here. So this is the watermark data set. This is after sorting and partitioning. And this is my region. All what I have to do is what? All what I have to do is compute the reference for each one of the partitions and then see if the number of points fall here or here. If they fall here, the bit decoded is 0. If they fall here, the bit decoded is 1. Then what do? I decode the bits. Then I map it to a map here. This map is 0 maps, this is the first bit decoded, 1 is the second bit decoded, 1 is the second bit decoded, and you see 3, and it keeps going. 0 is the third bit decoded. And if your watermark length is 6 bits, this means that the 6 bits will be repeatedly embedded in the relation. So how do you decide? It's by majority voting. For example, here you have decoded 0, 0, 1. This means that zeros have occurred the most. This means the decoded watermark is 0. Make sense? So here we are introducing some redundancy. We are embedding the watermark several times. Actually, it's a very famous technique, a very old technique in communication systems, which is referred to as repetition codes. Where, hey, I'm going to send you a bit, but every time I'm going to send you this bit, I'm going to repeat it n times. And then n has to be odd, so that if the number of errors happen is n over 2, you can still decode